Cool. Okay, so today we're talking about calculus. I'm going to do a super quick breakdown of the calculus that you need to know to understand gradient descent. Do also know that calculus in like colleges is like taught over 3-4 semesters. And what we're doing here is multivariate calculus, which is usually like the third semester of calculus. So a lot of these concepts can be, done in one dimension and then expanded. But, doing it in practice is very different, a lot harder. So hopefully what you get out of this is more of like a conceptual understanding of how gradient descent works. Gradient descent works differently for every algorithm, but the steps are very similar. So hopefully I go over the steps. Again, anything you need to clarify, please let me know. I do have like a list of things in front of me that I do want to talk about, so I have that structure there. But most of what I'll be doing, I'll be like drawing on this whiteboard. So two main things. I'm going to talk very overall about calculus and derivatives and what they mean, what they are. And then I'll move into gradient descent. So two overall sections. So first to start, let's start with derivatives. And we'll start here, derivatives. So what is a derivative? So usually when you have a derivative, you're taking the derivative of some sort of function, some sort of function. For example, if I have a graph like this that looks like this, you want to find the derivative of that. The derivative of a function is another function. What that means specifically, I'll get into. But if you evaluate the derivative at a specific point, so again, I told you derivative of a function, and this is not accurate, but the derivative of a function is usually another function. But if you evaluate the derivative at a single point, and let's call this point, I don't know, A, and let's say that this is also A. This is not accurate, by the way. And this is the derivative graph, and this is the function itself. In mathematical terms, it'll sort of look like this. This is the derivative on the right. Evaluating the derivative at a single point tells us the instantaneous rate of change of the function at that point. So basically this value here, we'll call this B. B is the instantaneous rate of change of the base function here at this point A. Does that make sense? So what instantaneous rate of change means is like how at this point, another way to interpret this is what is the slope at this point looking like? And of course, this is not really a straight line. You can't really calculate a slope. In math terms, what we do is we actually take a line and we sort of stick it to the curve, and that's what we call a tangent. And that is sort of a representation of how fast the function is changing at that point of time. So any questions with this so far? All right, easier to break it down first to a straight line. Let's say I had a function that looks like this. This is y, this is x. And let's just say this line is y equals to 2x. And what y equals to 2x means is, let's say this is 0. We start here at this point, wherever, whatever x is, y is just double of that, right? So x is 1, y is 2. At this point, x is 2 and y is 4. What is the rate of change of this? Like I mentioned before, when we were talking about derivative, we try and take a line and stick it to the curve because this is a line. The line that you stick to the line will be the line itself. So what is the rate of change of this line? More specifically, how is y changing with respect to x? So with every increase in one of x, you're increasing y by 2. Kind of sounds familiar because that is, those are the coefficients of what we're dealing with a linear regression, right? When we increase what variable by 1 unit, how does our dependent variable react to that? And that's really what a derivative is. If you had your linear regression function, like y'all were doing house prices before, and let's get rid of this for now. Y'all were doing house prices before, you end up with some equation that looks like price equals to some constant plus some beta 1 of, for example, square foot, plus some beta 2 of, for example, bathrooms, etc., right? if you were to take the derivative with respect to something like square foot, you can see the rate of change of square footage with your price. You increase square foot by 1, how does your price increase? The slope is sort of like your derivative. Questions about that? That sort of ties together what we were talking about with our linear regression. All right, so why is this important for us at this moment when we're talking about gradient descent? Something cool to notice is that when you have a function and you're finding its derivative, you're talking about a rate of change. So let's just look at this first function that we talked about. Let's ignore this inaccurate graph. The derivative tells us the rate of change. So for example, at this point over here, our rate of change is like a pretty positive looking slope. If we have something that's like decreasing, we have like a negative looking slope. One thing that people don't really think about that much is if we have like a minimum point over here, the slope is actually a flat line. And with a flat line, the derivative is actually 0. And that's something to remember. At any minimum or maximum point, so anything where, you know, when you're trying to stick a line to the curve and it becomes completely flat, like this would be one example. This would also be one example. Your derivative is 0. And it's pretty helpful for us because it gives us a more straightforward way for finding the minimum or maximum of some function. So that's like kind of like an overview of the calculus that you need to know. But any questions so far? I guess I can also mention this in this recording, but right before this, Ali asked the question of, well, when we find the derivative being 0, how do we know if it is a minimum or maximum? For gradient descent and what we're going to be talking about, for most of the time, it will always be a minimum point. The way that cost functions are built and are generated, usually it is a function that is always decreasing, so you come to a minimum. But several ways you can check if it's a minimum or maximum. First of all, if you take the derivative of the derivative, so that would be the second derivative, if your second derivative is positive, it will be a minimum point. If your second derivative is negative, it would be a maximum point. But also you can just literally take a look at the points surrounding your minimum or maximum to just check if it is a minimum or maximum and just compare the surrounding values. All right, questions before we move on to gradient descent?
Ish, can you repeat that last part one more time about taking the derivative of the derivative?
Yeah, absolutely. So let's say I have this function here, and with this function, I'll try to be a little bit more accurate with this one, but the derivative of this function crosses 0 a couple times. So I'm gonna guess it looks something like this, honestly. So at these points, and I'm gonna say that this point is A, at this point here, we don't know if it's a minimum or a maximum, because if something crosses, if the derivative is 0, it doesn't tell us, it tells us if it is a minimum or maximum, but it doesn't tell us which one it is. So one way that we can do that is we can actually take the derivative of the derivative. So for example, if this function was like a x cubed plus x squared, yeah, let's just say this is the function. Again, not accurate, not to scale. Our derivative would be 3x squared plus 2x. And then our second derivative would literally be just taking the derivative one more time. It would be 6x plus 2. If that makes sense. So we would just evaluate it at A, and this graph would probably look something like, let's see, I think it would go like something like this. But anyways, not super accurate, but this would be something like A. And if A is a positive number, it is a minimum. If A is a negative number, it is a maximum. So this kind of inaccurate, kind of somewhat accurate graph, you can see here the derivative is slowly increasing. If you don't really understand this part, it's honestly not a big deal for this. But yeah, you can see here that the derivative of the derivative would be positive, so it'd be a minimum point. But usually you would just evaluate, you would replace this with whatever your a value is, and if it's positive, it would be a minimum point. If it's negative, it would be a maximum point. But yeah, hopefully that helped. Honestly, not super important for this, knowing whether something is a minimum or maximum, but yeah, any other questions?
I'm taking notes. I don't quite get it yet, but I'm sure I will.
No worries, no worries. There's a lot of great videos explaining calculus. Again, like in college calculus, the taking derivatives doesn't even come in until like the end of the first semester. So not to worry at all.
Okay.
I think more important to understand is like the big picture of how gradient descent works.
Got it.
Which I will get into right now. All right. So we'll start our second part on gradient descent. All right. So gradient descent has a couple parts that are constant no matter what algorithm or model you're dealing with. So the first thing that you always have is a cost function. So cost function would be the function that's defined differently for whatever model you're choosing. We actually did deal with a cost function when we talked about linear regression. The cost function basically is something that tells us how well our model is fitting. I don't know if anyone has any idea of what our cost function with linear regression was. Any ideas?
Wasn't that the root mean squared error?
Yeah, exactly. The cost function for our linear regression was our root mean squared error. And what we wanted to do was to get the lowest root mean squared error between your points and the line. So if you imagine like, all right, let's say these were our data points and we want to fit this line, the best fit line, which is the line that, you know, stats models or scikit-learn's linear regression will spit out, will be the line that reduces the root mean squared error between the point and the line. So this is the cost function of linear regression. Basically, the cost function is defined with some mathematical formula that allows you to plug in values of your line and your data points, and it'll just calculate this RMSE value. So cost function is one big part of, it is the main part of every single gradient descent model. So this is also kind of why in stats models, this was called OLS, ordinary least squared. I think I mentioned this when we were going through it, but something I also said yesterday was that stats models uses the linear algebra way for solving linear regression that we did yesterday, by when you had like the X transpose, all of that. But scikit-learn does the gradient descent method of solving for linear regression. And in explaining that, I'll talk about the next two parts of gradient descent, which are initial values and then our learning rate. Okay, so we're going to be looking at a couple things simultaneously. So with gradient descent is sort of it ends up being more efficient, even though it doesn't seem like at first. It ends up being more efficient over time as cost functions get more and more complicated. So how gradient descent works, first off, you have to define some initial values for what you're trying to figure out. So in a linear regression, remember that what we were trying to find were our parameter values, right? Like what were all our betas? What were our intercept and our coefficients? Those are what we're trying to find. With gradient descent, you always start with some arbitrarily decided initial values. For different models, you actually get to input different initial values. I believe that linear regression actually starts with an intercept of an average and everything else at 0. I believe that's how it works. So what that means is our initial line that it's going to test out first is a flat line like that. And so this line would have a model of y equals to, and let's just call this a plus whatever betas, and actually right now betas are zeros, multiplied by x1 plus beta 2, x2, and so forth. So this is our initial value. These are our initial values for our first step of gradient descent. And with that, we can actually calculate our first RMSE. And obviously our RMSE is gonna be relatively high relative to that best fit line that we had. And so we're gonna actually take note of what this RMSE value is. So in this other graph on the side here, I'm gonna draw here. I'm gonna do RMSE. And here I'm just gonna do, let's do slope. Or actually, no, let's not do slope. Let's just do iteration for now. So at our first iteration, RMSE is gonna be fairly high, right? Because this is just the average line. Your mean squared error is gonna be much higher than if you were to give it like a tiny slope for now. So what it does is gradient descent takes note of what this initial RMSE value is. Then with the learning rate, it sort of thinks, okay, with this initial value, and let's actually not start with multiple dimensions. Let's just do like a slope and an intercept. Usually they do slope and intercept simultaneously, but let's just look at changing. Let's just look at changing the slope for now. So let's say, all right, here we have a slope of 0. So right now beta 1 is 0. How can we improve this model? With this RMSE and linking back to the equation, based on this learning rate that you've defined here, and for different models, the learning rate is at different scales, so you do have to look up documentation for that. With some learning rate, you're gonna shift your beta 1 such that you get a different line. So let's say, all right, maybe let's get, instead of this line here, let's perhaps fit a line that sort of looks like, let's do something that's not super accurate for now, but maybe something that looks like this. And then once it's refit the line and like given it a little bit of a slope, it'll recalculate RMSE. And so let's get rid of these green lines. It's gonna recalculate RMSE and take note of that as well. Hopefully RMSE goes down. Sometimes you might have RMSE go up and then it just knows to switch the direction of the way that the slope is being changed. So for example, if the points were going the other way and at first you increase your slope, it sees that your RMSE increases, it will know to decrease your slope next. So based on that, ideally, your RMSE starts to go down. So this is iteration 1, iteration 2. Your RMSE will start to go down. And because of your learning rate, it will keep adjusting your slope line closer and closer to the correct values. And how it knows when that happens is typically when you fit your line, all we're doing is we're gonna keep increasing our slope until it fits the line nicely. So let's pretend that this green line that I'm about to draw here, let's say that's our best fit line. So with our best fit line, we calculate RMSE. Let's say we've done this a bunch of different times. Usually the slope kind of looks like this because you slowly start to get better and better. Let's say we get to our best fit line here at iteration number 7, for example. At iteration 7, it's going to keep doing that because at that point, it doesn't know that iteration 7 is the best. At that point, it's going to keep increasing the slope. And at some point, RMSE is going to start going up again, right? You imagine we're increasing the slope, so it gets more and more steep. At some point, and I'm going to use this red line to show, at some point, the line's going to go maybe something like this. And the RMSE is going to go up again. So it knows that, all right, we've overshot our best fit. So we have to look back and see where our cost function had this minimum. So to tie it all back together, our RMSE from whatever initial values we had slowly decreases and then starts to increase again once it surpassed the best value. So what we actually do here is we're trying to find the value where our RMSE, our cost function, has a minimum. Does that make sense? Any questions about this so far? Right, so that's pretty much how gradient descent works. On a wider scale, it's actually using a combination of linear algebra and calculus to do this in all dimensions at the same time. because, you know, you can imagine, all right, let's say I tune the intercept first. I get the best intercept, but, you know, this is the best intercept for this lousy slope. So you kind of have to tune them both together at the same time. So that's a combination of multivariable calculus, which is really just doing this in multiple dimensions at the same time, which computationally you never have to do, as well as a combination of with linear algebra as well. But questions?
So,
Mhm.
Hi. So basically, you calculate this graph with the RMSE, and then you just find where the derivative is 0, and then that's what it does.
That's right. Yeah, sometimes not as simple as that, because sometimes these cost functions can get really, really complicated. So literally what they're doing is they are refitting your model over and over again. And again, this works differently for different models. I'll go into like more general speaking later on.
How
But
does it know,
sorry?
how does it know where the y-intercept is? To start?
Yeah, so to start, you would set some initial values. So if I believe in linear regression, it sets it at 0, 0. So literally your very first line is going to be like flat across down here. And what it's doing, it's both moving the line up and down and changing the slope of the line at the same time to figure out what the best slope and intercept is. So you imagine, I don't think many of you ran linear regressions that were that many dimensions, but if you were to run linear regression with like hundreds, maybe thousands of features, it will take a long time because it is adjusting like 1,000 dimensions at once. If that helps. So your cost, sorry?
Sorry, that's quicker than the way Stats Miles does it.
So stats, it really does depend actually, because stats models is doing a bunch of linear algebra. Matrix multiplication is a very computationally heavy process as well. So I think as you get bigger past a certain point, at very big data sets, gradient descent becomes more efficient than trying to solve for the actual values with a single equation.
Okay.
I don't know what that point is, but I mean, with your projects, I think you can't really tell the time difference between the two because they were both pretty immediate, but you'll actually see with, especially with algorithms that we'll be talking about next week, some of them will take minutes, hours to run, depending on how big your data set is.
Thank you.
You're welcome. Anything else? Yeah, so this is kind of where like the calculus comes back in. Here with this graph on the right side, you sort of see, you know, we're adjusting our model with different parameter values. That's the main point. We're using different parameter values of like different intercept and slope values to see what fits our model best. And the way we keep track of the best parameters is with this RMSE curve. You can sort of imagine once you have like more dimensions, let's get rid of this for now. If you have more dimensions, I'm bad at drawing, but imagine we have this other dimension flat on the ground. So let's say this is like square foot, and this is the coefficient for bedrooms. So instead of this green graph here, you'll have a curve that's going in 3D that, I don't know if I can draw this, but it'll sort of be going out like that. And then you're going to be changing both of these at the same time, and you're going to find like a minimum overall. That makes sense. See if you can find a minimum in all dimensions. But yeah, it gets kind of abstract with more features, but the concept is the same. You always have these three parts of gradient descent. You always have a cost function, and for all of the algorithms that I will be talking about, I'll be mentioning the cost function for each of them. You always set some initial values. Depending on the model, they have different options for initial values to start. Sometimes you can say force it to 0, force it to 1, force it to like the average or random as well. And then you set the learning rate. So learning rate is another interesting thing to tune. So in future models, you will get to choose, all right, I want this model to learn faster or slower. Learning rate, if you set it to be too small, it's going to take a very, very long time for your model to find the optimal parameters. But if you set your learning rate too big, you run the risk of overshooting your best parameters. So imagine if your learning rate was really big, your first iteration might end up being, all right, let's get rid of this for now. If you set your learning rate too big, and this is the cost function here, your first iteration, all right, you have this RMSE. Your second iteration might be here. Third iteration, even though this is the best, oops, how do I undo that? Even though this is the best value, your third iteration might be here. And they say, all right, it's still overall better. It will go on searching here, realize, all right, we got to backtrack now. And it's going to also, in some way, take a longer time to figure out. And it'll probably do something like going back and forth before figuring out, all right, this is the best value. So learning rate is something that you will be able to tune in almost all the models, I'm pretty sure. All right, questions so far before I talk generally about other models that we'll be talking about.
Would you change the learning rate based on the situation?
Yeah,
Like
definitely.
what situation, why would it make a difference? Should
Yeah,
it always mathematically be faster one way?
Yeah, so learning rate is actually something that is hard to say because you can make an informed decision if you understand where learning rate comes in your cost function. So learning rate is actually part of how you determine your cost function and your parameters. So if you understand like your formula, then you can make a more informed decision. I will say even I pretty much just test a few different learning rates just to see what gets me to my optimal value. So I don't even look into the formulas that deeply. I will say pretty much only like machine learning engineers at a high level do that. Learning rate is something that if you're running, let's say model A, what you would do is you would run model A 3 times with 3 different learning rates and just see what gets you your value either faster or a more accurate prediction. So it's complicated because if you want to make an informed decision, you would have to understand the math, but not complicated because for data scientists, all we have to do is really just run the model and find the best results. The way we build the model for data scientists is a little less important.
Thank you.
You're welcome. Anything else? Okay, so every single machine learning algorithm that we will be talking about has a cost function embedded in some part of the algorithm. So starting tomorrow we'll be talking about extensions to our linear regression model. We'll be talking about 2 other models that are very similar to linear regression, but take into account overfitting, which is pretty cool. And they both have cost functions, which I will mention in showing how it takes overfitting into account. But anyways, every algorithm that we'll be talking about has cost function embedded in some part of it because every model works quite differently. For each of them, initial values and learning rate are actually parameters that you can set. And yeah, let's see. That's actually pretty much it. I expected more questions, to be honest. But yeah. Gradient descent is a pretty common question that is asked. Usually you don't need to like know formulas about this, but if you can do like a 1-minute explanation of how gradient descent works, like for a model, you're trying to find the best parameters, you start with initial values and then try and get them better. That works. See. Sarah, I see your message that your microphone isn't working. So feel free to type in your questions. We do have some time, but if not, I can always address them tomorrow because we also have our one-on-one tomorrow, I believe. But yeah, any other questions? Is anyone like really, I don't know, does anyone feel like really intimidated by all of this math stuff? I can imagine. I hope not, but I will say that, yeah, I definitely benefited by having studied math in college. I know not everyone is the same, but I will say like it doesn't affect, like you don't have to know like the deep math until you get to like a higher level of like machine learning engineering as a data scientist. And we'll see throughout the processes that we're going to go through this project, it's more of evaluating and interpreting models, just like we were doing with our last project. We're just running models. We don't necessarily need to know like the exact algorithms of how they're deciding the best fit line, but it's more about interpretation and explanation of like why you decided to do this in your modeling
I have a quick question.
process.
So you said that if the learning rate is too fast, then you risk overshooting your minimized function. But how would you know that from the results? Like, how would you be able to tell that you actually skipped something that's more accurate? Because if it's less than what you saw before, it would seem accurate. So.
You're right. Yeah. So it's one of like the pros and cons of scikit-learn. The fact that it's quite opaque and it does everything for you. Scikit-learn does all the does the gradient descent for you within each of their models. So you'll literally call like model.fit. You will maybe set the learning rate when you instantiate the model, and you won't know. And to my knowledge, you cannot even extract like the cost function values at each iteration. And so that's sort of something that honestly, you probably won't know. You sort of can have an assumption. That's why typically you test different learning rates for each model. So yeah, not a direct answer. I guess the answer is you can't know through scikit-learn. At least to my knowledge, you can't extract your RMSE values to see like, you can't like plot your graph and see how it works like this. But yeah, to my knowledge, you won't really know, which is unfortunate. But yeah, I think one thing that, I think I was telling this to someone yesterday, but one thing that was kind of funny is that there used to be like a rivalry between software engineering and like data scientists, because people are saying that like data scientists can't code because all we do is like, we just run a lot of code. We're just running the code and running the models. Whereas software engineering, what they're doing is pretty intense. Like, you know, they're literally like writing things from scratch, where we're just like repurposing a lot of code, running models, and all we're doing is really interpreting, which I guess kind of true. But yeah, I don't know where I was going with that, but I guess the point is, for our job is more, especially entry-level data scientists, our job is more on the interpretation side, not so much like constructing your own brand new model. Yeah, any other questions?
This one might be a little bit more meta, but
Yeah.
Like a local minima, how do you know that there are not additional local minimas that you're missing?
That's a really, really good question. That's actually a question that was asked the last time I gave this lecture. So the way that cost functions are generated, usually most cost functions are written and defined in a way where you won't have multiple minima or maxima. Yeah, so therefore, what's the word? I can't think of the word. It's not monotonically decreasing. Oh, I guess the first derivative is monotonically increasing. If that doesn't make sense to anybody, basically all cost functions are written to have this kind of shape. And by this kind of shape, meaning like it's gonna start high and then get worse and then start getting better. And what I mean by monotonically increasing, I don't know if I need to get into this, but you can sort of see here, the slopes here start steeply decreasing. And then it sort of gets less steep, less steep, less steep. So it's actually starting super negative, gets less negative, gets to zero, and starts to get positive, positive, more positive. So therefore you can see that the slope is numerically always increasing. So because of that, you're only gonna pass zero one time. And typically cost functions, at least to my knowledge, cost functions are written in a way that you don't have multiple minimum points. Yeah, that's a good thing to consider. Anything else?
I have another one out of left field if no one else has questions.
Okay.
I was looking at the StatsQuest video of principal component analysis, and they were talking about maximizing the distance between the points when they're reducing the dimensionality. So is that an example where they're looking for the local maxima, or is it just a totally different topic?
In some way, yeah, because the cost function can be defined in a different way where they're trying to like, I guess you can optimize it in a certain direction. So here in optimizing, we're trying to reduce this cost function. And I guess the way that you would think about defining that kind of cost function would you want to have a maximum of this value, which in the same way the function should be the derivative of the function should be monotonic. PCA specifically, very interesting, is actually a linear algebra method of deciding what the best deciding on the principal components is actually done by matrix decomposition of the covariance matrix, if I'm not wrong, which is super cool. It is actually classified under unsupervised learning, which is the beginning of phase 4. So not to worry about for now. I will actually mention PCA very briefly during an office hour because I think for some of your projects, it might come in handy, but we won't go into detail until phase 4. Yeah, anything else? Cool. One thing to just like wrap up these 2 math topics, if all of this was like, I have no idea what's going on, it's fine. I do think like a lot of the labs, they have you code a lot of things from scratch, especially for this section. I think that, if you don't intend on becoming a machine learning engineer within the next year, you don't have to fully understand the math that goes behind like gradient descent and all of that. I think what's good to know, especially to prepare for interviews, is explain in a minute briefly to like a kind of non-technical audience what is gradient descent and how does it work. I think if you can understand that, that will be fine. And that does come more calculus than linear algebra. So for the next few topics, everything from 24 up to like 31, we're going to be talking about different algorithms with different cost functions that do gradient descent in kind of the same steps, but slightly differently. And so when we get to those, I'll talk about that. But yeah, if there are no other further questions, I guess I will see you all at tomorrow's study group. And yeah, if anything comes up, as usual, feel free to send me a message on Slack. Yeah, I will see you all tomorrow and at your project reviews. Bye, everybody.
Bye, thank you.
Thank you, bye.